Okay, does that make sense a little bit? Okay, so reading plots is not easy, but hopefully we'll get used to it very soon. Okay, so actually let's say, okay, so I want to point out one thing. The contour plot tells us actually what happens when we move, when we change x and y. So if I change the value of x and y, that means I'm moving east, west, or north, south on the map. And then I can ask myself, does the value of a function increase or decrease in each of these situations? Well, that's the kind of thing that the contour plot can tell me very quickly. So okay, so say, for example, that I have a piece of contour plot that looks like that. Maybe this is f equals 1, and this is f equals 2, and here this is f equals 0. And let's say that I start at a point, say at this point. Okay, so here I have x0, y0, and the question I might ask myself is, if I change x or y, how does f change? Well, the contour plot tells me that if x increases and I keep y constant, then what happens to f of xy? Well, it will increase, because if I move to the right, then I go from 1 to a value bigger than 1. I don't know exactly how much, but I know that it's somewhere between 1 and 2. It's more than 1. If x decreases, then f decreases. Okay? And similarly, I can tell that if y increases, then f, well, looks like if I increase y, then f will also increase. And if y decreases, then f decreases. And that's the kind of qualitative analysis that we can do easily from the contour plot. But maybe we'd like to actually be more precise than that and tell how fast f changes if I change x or y. Okay? So to find rates of change, that's exactly where we use derivatives. So we are going to have to deal with partial derivatives. So I will explain to you soon why partial. So let me just remind you first, if you have a function of one variable, then, so let's say f of x, then you have a derivative, f prime of x, is also called df dx, and it's defined as a limit when delta x goes to 0 of the change in f. Sorry, it's not going to fit. I need to go to the next line. It's going to be the limit as delta x goes to 0 of the rate of change, so the change in f between x and x plus delta x divided by delta x. Okay, sometimes you write delta f for the change in f divided by delta x. Then you take the limit of this rate of increase as delta x goes to 0. Now, of course, if you have a formula for f, then you know, at least you should know, I suspect most of you know, how to actually take the derivative of a function, from its formula. now, how do we do that? Oh, sorry, and I should tell you also what this means on the graph. So if I plot the graph of a function, and I have my point x, and here I have f of x, how do I see the derivative? Well, I look at the tangent line to the graph, and the slope of the tangent line is f prime of x. Okay? And truth in advertising, not every function has a derivative. You have functions that are not regular enough to actually have a derivative. So in this class, we are not going to actually worry too much about differentiability, but it's good at least to be aware that you can't always take a derivative. So, yes, and what else do I want to remind you of? Well, we also have an approximation formula. Which says that, if we have the value of f at some point x0, and then we want to find the value at a nearby point x close to x0, then our best guess is that it's f of x0 plus the derivative f prime at x0 times delta x, or if you want, x minus x0. Okay? Is this kind of familiar to you? Yeah, I mean, maybe with different notations. Maybe you called that delta x or something. Maybe you called that x0 plus h or something. But it's the usual approximation formula using the derivative. If you put more terms, then you get the dreaded Taylor approximation that I know that you guys don't like. So, okay. So the question is, how do we do the same for a function of two variables, f of x, y? So the difficulty there is we can change x, or we can change y, or we can change both. And presumably, the manner in which f changes will be different depending on whether we change x or y. So that's why we have several different notions of derivative.